Now we'll finally come around to talking about spectroscopic parallax. This is a method of determining the exact distance to a star by analyzing the relationship between the star's apparent and absolute magnitudes. Now, this is not to be confused with the visual parallax effect that we used as the basis for stellar parallax. This one's different. We follow these steps for the spectroscopic parallax process. First, you look at the star. Whether you look at it in reality or you look at it online, it's totally fine. Just look at the star and determine its apparent magnitude. Now, don't worry about having to come up with a value of your own for the apparent magnitude of the star, because chances are the apparent magnitude has already been determined and you just need to look it up online or in a book or a catalog. Then we'll determine the spectral and luminosity class of the star, which is also most likely already predetermined for a lot of stars, and we'll plot it on the HR diagram. This will yield the star's absolute magnitude. Now we have to compare the apparent and absolute magnitudes to calculate the exact distance using the distance modulus. It can come in either of two forms, one where we have the apparent magnitude minus the absolute magnitude equals 5 times the logarithm of the distance to the star d minus 5. But we need to solve for d, the distance. Thankfully, that's already been done too. So the distance modulus can also be written as d equals 10 to the power of apparent minus absolute magnitude plus 5 divided by 5. Now this entire fraction is the exponent, so it's 10 to the power of that fraction. Keep that in mind. Let's find the distance to Sirius, an A15 type main sequence star, using spectroscopic parallax. So we've looked at the star, determined its apparent magnitude, thank you Wikipedia. So now we must go to the HR diagram and find Sirius on it to find its absolute magnitude. Now that we have that, we can head over to our notebook and start working through the math. So we know the apparent magnitude of Sirius is negative 1.46 and the absolute magnitude is positive 1.42. We'll use both these values in the distance modulus, where the lowercase m is the apparent magnitude and capital M is the absolute magnitude. So let's begin. D equals 10 to the power of apparent minus absolute magnitudes plus 5 all over 5. Plug in the values we have for apparent and absolute magnitudes in their respective places. I'm putting the absolute magnitude in parentheses to remind myself that regardless of the value for the absolute magnitude, whether it's positive or negative, I have to subtract it from the apparent magnitude. The numerator of my exponent becomes 2.12 when I add up all the numbers, and then I have to divide that by 5, which gives 0.424 as my exponent. 10 to the power of 0.424 is about 2.6546, and the units I have for my distance are parsecs. They'll always be parsecs if I'm using the distance modulus. So rounding to 3 significant figures, I get 2.65 parsecs. But how much is this distance in light years? Remember, 1 parsec is equal to 3.26 light years, so we'll use that as our conversion factor. 2.65 parsecs times our conversion factor, with 1 parsec in the denominator to cancel out the parsec in our original number, and 3.26 light years in the numerator. So we multiply 2.65 by 3.26 and get 8.654 light years. Rounded to 3 significant figures again, since we only had 3 significant figures in either of the 2 original magnitude values, we have 8.65 light years. So let's compare these values with those given for the distance to Sirius. Not bad. It's close enough. These values on the Wikipedia article for Sirius were calculated using stellar parallax, but it goes to show that spectroscopic parallax is effective in determining distances to stars as well.